Hi everyone. So next topic is regression splines. So remember that we have studied step functions. So step functions are polynomials with degree 0. But in general, we can define piecewise polynomial functions. So suppose that the domain of x is split into two parts. X is smaller than c and x is larger than or equal to c. And the step function only uses constant to represent y. But in general, we can have straight line or even cubic line or cubic curve or quadratic curve or cubic curve. So this is more general case than step functions. Sometimes if we go more than step functions, we want to make the entire function continuous. So this imposes the some constraint on coefficients. For example, in the case of this cubic function, if we have not point C and we have observations, even if relationship for this range and this range are different, still usually we want to fit two curves so that two curves are continuous at point C. The regression spline is a more sophisticated method to impose continuity as well as the same derivatives. For example, sometimes we want to impose derivative at C is the same for both curves. If derivatives are the same, then we have smooth curve, or even we can require the second derivative are the same. So in general, we require the continuity as well as the same derivative of a specific order at not points C, so that function for the entire x is smooth enough. So this is illustrative example. So if we don't have any condition on two polynomials, for example, cubic curve for each region, cubic curve may be this. But if we impose the continuity, the curve becomes this. This have one constraint, so basically we lose one parameter here, but it looks much more plausible. If we require also the first derivative is the same, we can get this kind of the smooth curve. Actually, the cubic spline also requires second derivative are the same. Of course, if each component is simpler function such as linear function, we can only require continuity at C and that we have to compromise the first derivative. So again, for smoothing spline, the one difficulty is decide not points. So smoothing spline solves this issue by using many not points and imposing penalty on smoothness. So the idea is that even if relationship is complicated, if we have not points between every two observations, we can express very complicated relationship. But if relationship is very complicated, still we want to make the curve somewhat smooth. So we want to put some penalty if the curve is not smooth. Suppose that this curve, fitted curve is g of x, And smoothness is represented by the absolute value of g double prime, second derivative. So to make this positive, that we take square and that we define this integral as the smoothness of g of t. Then we want to minimize error size, sum of squared errors, plus some constant lambda times smoothness. So this criterion balance between error size and smoothness. So this is the same concept as lasso or rich regression. So here lambda is hyperparameter. So this is non-negative parameter. So we have to optimize it by cross-validation. So this is one data example. So data is the same as the last time, the wage on age. We have two smoothing splines. So one is 16 degrees of freedom and the other is 6.8 degrees of freedom. So second one is actually optimized by leave one out cross-validation. So this is optimal case. So you can see that both curves are very smooth because we impose the same derivative and the same second derivative and continuity at each knot points. We cannot even notice where is the knot points. But you can see that the blue curve looks slightly better than the red curve because red curve they unnecessarily fluctuate. Basically because we have too many knot points and too many degrees of freedom. Okay, so now you can go to quiz 324 3 2 1 and you can solve next question. Okay, see you then.